Thank you very much for joining us tonight for our sixth CPD event organized by the Institution of Structural Engineers and hosted by American University of Dubai. Welcome to all with us in the room. Apologies for the slight delay, maybe not so slight. Thank you for your patience while waiting for the IT to be set up. For those who are in the room tonight, just a quick housekeeping note. There is no fire drill tonight, and if the fire alarm goes on, you need to go out from this door to the right, all the way straight outside to the soccer field. There are some refreshments outside if you'd like to help yourself anytime. We will be taking questions after the talk, here live in the room, and also if you'd like to drop your questions in the Q&A chat box on Zoom and YouTube, where we are streaming live and recording the session as well. I would like to thank our sponsor, Ramboll, who is a supplier of intermittent fire paint and fireproof and durability paint, who is our sponsor this year. I would like to also thank very much AUD for the organizing the venue, the logistics, and all the work that and also for bearing with us, postponing the event from the day where we had severe flood in Dubai to tonight, promise no floods, hopefully. Introducing our speaker for tonight, our talk will be on prefabrication of tall buildings. Obviously a topic that is revolutionizing our construction industry, helping on increasing efficiency, speed, quality control, safety, and also helping on sustainability, reducing embodied carbon and reducing waste. And our speaker for tonight is Alessandro Marzucchini from Ramboll. Alessandro is a chartered structural engineer with experience in the design and management of projects, particularly high-rise buildings. Alessandro leads the MMC services at Ramboll, including the FMA offsite and modular construction across various projects, particularly complex structures and high-rise buildings. Alessandro is also active in research projects and collaboration with universities. His projects span over Singapore, where he is based, Southeast Asia, China, Middle East, India, and Europe. So Alessandro will take us tonight through the design principles, will take us through the latest technologies, some of the challenges and constraints, particularly those pertaining to our Middle East region. I'm sure it will be a great talk. Thank you very much, Alessandro, and I can hand over to you now.
Okay. Thank you, Iman, for the very good introduction. Good evening, everyone. Thanks for joining today in person or remotely. Thankfully, the weather is good today, and we can finally have this talk. It was initially scheduled 2 months ago, and then due to the bad weather and the flooding, we had to reschedule for today. So today's talk is about prefabrication in tall buildings. This is a topic which is very relevant in the industry, and particularly to the Middle East region, because we are seeing a lot of countries in the region which are currently experiencing rapid urbanization. So prefabrication holds the potential to help in reshaping the future of the built environment, and that's because it can overcome some of the key challenges that we are facing. So today we will discuss, first of all, why is prefabrication such a game changer when it comes to design and construction, particularly for tall buildings. We will also discuss what is the design considerations that take into account and how different these design considerations are from the design principles that apply to more conventional construction methods. And we will do that by looking at some case studies which showcase the successful implementation of off-site manufacturing technologies for real projects. And finally, we will do some reflections about the state of the art of prefabrication, but also about what are the current barriers that prevent the wider adoption of prefabrication and modular construction within the industry, and what are the opportunities that lie ahead of us. We will also see that prefabrication usually is a term that comes with other terminologies often associated with it. We often hear about MMC, modern methods of construction, but also modular construction, DFMA, design for manufacturing assembly. So today we will familiarize with all of these different terms. So without further ado, let's get started. And let's start off by asking ourselves the number one question we should always ask when we try to innovate and change the way that we've been doing things, which is why? Why prefabrication? Why is there a need to change how we have been designing and constructing structures and buildings for decades? To understand that, we should take a step back and look at conventional construction methods to really identify what are the key challenges associated with it. Conventional construction encompasses several methodologies and different materials, but those usually have a common denominator, which is in situ works. In situ works means that we build structures and buildings which are already on site and in the final configuration. Now, typically, projects that utilize conventional construction face issues related to the time intensity, but also the high amount of labor which is required on site. Now, these two factors are often associated with a level of unpredictability of events that can happen on site, such as delays due to the weather conditions, for example, like flooding, or due to the procurement of material. So all of this usually results in low efficiency of the sites. We also have additional issues such as the high carbon footprint, as well as the high level of noise and construction waste. So all of these problems that we face with conventional construction typically result in low productivity, as well as low quality of the products that we can achieve. And last but not least, a huge environmental impact. So in this kind of scenario, that's where prefabrication comes into play and helps us. And if we take a step back and look at MMC, which is modern methods of construction, that is the broader approach. And what MMC does is that interesting fact about MMC is that it doesn't try to solve the specific issues of the industry, but instead is rethinking the entire approach much more holistically by looking at all the aspects from design, construction, manufacturing, assembly, and even rethinking the engagement models and the collaboration with all the stakeholders which are involved during the project. And often with MMC, we also hear about prefabrication. Now, why MMC is focusing on the approach, prefabrication instead is about the process, and especially is the enabler for this radical shift from construction sites to assembly sites. And that happens through off-site manufacturing. Now, talking about technologies which are available, there is quite a wide range of different systems that we can rely on in terms of prefabrication. And those can be grouped into macro categories by system typology. There are particularly three types of macro categories. Number one is elements, also called kiloparts. In this case, we have single components such as slabs, beams, columns, or walls, which are prefabricated in a factory. And once prefabricated, they are transported to site for installation. This can use different materials from reinforced concrete, steel, timber, or composite materials. And usually, this is among the three different system typologies, the one that's been in the industry for the longest time, and for which we can rely on a well-developed supply chain. But usually, this also comes with quite an amount of work to still be done on site, such as the MEP installation, architectural finishes. So a way to push the elements further is by looking at volumetric. In this case, we don't just prefabricate single components, but we also pre-assemble those to form complete volumes. And to take volumetric one step further, we can extend the pre-assembly of the volume, not only to the structural components, but also to the MEP, architectural finishes, so that the volumes will be pre-finished. And that's what usually we call in the industry prefabricated, pre-finished volumetric construction, PPVC. The advantages are really maximizing the benefits of speed, quality, safety, sustainability, but usually comes with some constraints, such as a reduction in clear ceiling height, as well as some loss of floor efficiency, for example, because of a double column situation or a double wall. So those are important considerations that have to be taken into account by all the designers and consultants who work from every stage of design, so that we can come up with a very well-developed and coordinated design solution which can correctly implement the technologies on board. Another constraint would be the logistics as well that have to be taken into account. Now, the third typology is the hybrid. The beauty about the hybrid is that it brings together the advantages of elements and volumetric. We still prefabricate single components, and we want to also pre-assemble them, but they don't have to form a complete volume. It could be that, for example, we can have a floor which is pre-finished and pre-installed to a prefabricated facade, and then at that point transported to site for installation. Or we may be looking at a prefabricated bathroom pod or kitchen pod, which is prefabricated off-site, transported to site, where it will be installed together with the kilo parts of column, beams, and slabs. So doing that gives us more flexibility on the design, and at the same time, we can still obtain all the benefits of speed, quality, and safety. So it's really a way of overcoming some of those constraints which are often linked to volumetric construction. Now, speaking of flexibility, we also have material flexibility when it comes to prefabrication. We can build systems utilizing steel, concrete, timber, or hybrid materials. For example, we may be looking at designing a volumetric component where we want to use a lightweight flooring system, for example, in order to ease the logistics by reducing the module weights. But we could have a balcony which is already pre-installed to the module from the factory, and the balcony will be subject to more aggressive environmental conditions. And in that case, we want to use a more durable material, such as reinforced concrete. So mixing and matching different materials gives us a flexibility to meet the project-specific requirements, but still maximizing the use of the materials available. Now, talking about benefits, we quickly went through this just now with the system typologies, but let's delve into this in more detail. The number one advantage often that comes with prefabrication, and it's probably the most fascinating, is the speed of construction. By concurrently prefabricating off-site and also enabling the works on site, we can really maximize the speed, which is particularly beneficial, especially for those projects which are located in densely urbanized areas subject to further urbanization, where speed is a key driver for the project. Additionally, we also have the quality to be achieved by shifting the construction to a controlled environment, and also the safety which can be obtained because of the control environment, so that the workers will be working with a less hazard. But also we have sustainability, which is another important aspect. Sustainability is very important, especially in the climate crisis that we are currently witnessing. Sustainability can be achieved from many different fronts, from minimizing the construction waste, as well as reducing the energy consumptions due to the on-site activities, but also by preserving the biodiversity with less disruptive construction sites, and ultimately reducing the carbon footprint. And this can be done particularly because prefabrication helps us promoting more carbon-friendly materials. So we can shift the construction towards materials which are innovative and more carbon-friendly compared to the materials that we normally use for conventional construction. Also, reduction of disruptions. This comes especially when regarding the noise disruption, particularly important for those sites, those projects which are noise sensitive in dense urbanized areas. This is probably a good summary of those benefits which are the more tangible ones, those benefits that we can really see at the project level. But there are also additional advantages which come with prefabrication, which they are not as tangible at the project level, but we can benefit from that at more of a society level. And this includes socioeconomic growth. We can use prefabrication to actually create socioeconomic growth to the country itself. That can be done by upskilling our workforce to become highly specialized workforce. And by doing that, we can do this, for example, through training and education. And by doing that, MMC and prefabrication can become the catalyst for the country's growth. And that's particularly important, especially in those countries which are growing economies. Also, resilience that we can achieve, we can build more resilient cities. And that's because of the quality control of the products that we obtain from off-site manufacturing, but also because we can design and construct in high seismic zones. So using prefabrication helps us build more seismic resilient cities. And ultimately, we have adaptability. Using prefabrication helps us to build more adaptable structures and buildings, and that's very important, especially in today's society where the there are continuous changing in the requirement. Now, with this overview of what is MMC, what is prefabrication, what are the key benefits, let's now talk about what are the design considerations. And we will do that by looking at a few case studies which showcase the successful implementation of prefabrication technologies. Over the years, Ramboll has done a number of projects in different geographies and continents, and those projects encompass all the systems that we have seen just now in the previous slide, from kit of parts to volumetric construction. In the next couple of case studies, we will expand on a couple of these projects to really see how we have managed to use different system typologies to adapt to what are the project-specific requirements. The first case study takes us to Hong Kong, where we recently completed 20-story building for the University of Hong Kong. It's a student accommodation. It was built in 2023, so almost 1 year ago, and it includes 20-story towers, 2 towers, 17 stories of which are modular volumetric construction on top of a 3-story conventional podium and foundation. In this project, by starting at the early stage of design and working together with all the design and site consultants on board, we managed to achieve efficiency. As you see in this table, to summarize the number of modules that we delivered, the almost 1,000 modules with only 5 sizes of module variations from M1 to M5, where a module size identifies the module chassis in width, length, and height. So what you see is that we achieved high repeatability and a minimum number of module size variations. So that allows us to achieve cost effectiveness through economy of scale. It's important to note also that within a certain module size, M1, for example, we have also substructural typologies, which means that we identify different structural components and optimize, for example, the column weights, so that we also optimize the materials while also preserving the standardization. So it was really about finding the sweet spot between standardization and optimization, which are often competing parameters. Now, the next case study takes us back to Dubai, where we did a collaboration with Link, which is the modular division of Alec Contracting, and the collaboration also saw the involvement of Imara. In this particular project, we developed a modular building system which would be suitable for multi-story buildings. And as part of the system development, we also went through the process of obtaining the Dubai municipality in principle approval for the modular building system. So as part of the development of the system, we wanted to put the system in the context of a building, and therefore we also studied the case study, which was an Imara residential building designed and constructed using conventional construction, and we modularized. So we converted into modular. We saw what to do in order to make it efficient for modular construction. So particularly, we identified areas of the building which are suitable for modular volumetric, which are the apartment areas. And this was combined with other areas, which are the core areas, which instead are providing lateral stability for the building. In these portions of the building, we located the reinforced concrete shell walls, which could potentially be prefabricated shell walls, but essentially there is a dedicated area of the building which provides lateral stability. Now, often when it comes to volumetric construction, for high-rise buildings, we want to have this combination of systems, modular volumetric together with a lateral forcing system. And the reason for that is because it allows us to release the modules from the lateral forces. So the modules will still be load bearing, but they will just be taking the gravity forces from permanent and variable loading. Whereas the core walls, in this case, will take the lateral forces from wind and from earthquake. Now, it's important to note that even in this combination of systems, lateral force resisting system, together with the volumetric construction, the modular volumetric still plays an important part when it comes to lateral stability. And that's because the modules have to enable a load path which allows the lateral forces to travel from module to module to module and back to the main lateral force resisting system. So the modules will act as rigid or semi-rigid diaphragms, transferring those forces from module to module. And In this context, you can see how important the connections between the modules are. And that's what usually we call inter-module connections. These are usually of two types. There is a vertical connection, which connects the module below to the module above, and then there are horizontal connections, which connect two adjacent modules at the same floor and take those in plane forces from diaphragm forces from wind and from earthquakes. Now, on the screen, we see a typical example of connection in case of modules utilizing steel chassis, but if we have RC modules, same principles still apply. Now, as part of the design process, we start off with the global analysis through which we analyze forces, reactions, lateral drift and deflection, but then we get to the element design and finally to the connection, intermodule connections, and we can do additional localized finite element analysis and modeling and design in order to understand what are the forces and stresses which develop within those connections and ensuring that they are within the limits and comply with the code requirements. Especially in regions like Dubai and in seismic regions, it's very important to ensure that we achieve activity on such connections, which is a very important characteristic for buildings located in seismic region. Now, another important aspect when we look at prefabrication, design of prefabricated system, and particularly for modular, is design for logistics. That means that we have to understand what is the module weight, and we can do that by developing the design to a level that we are aware of what are the components from a structural point of view, but also MEP architectural, because for volumetric, often all of this will come together from factory. And that's important because the weight of the module, as well as the size of the module, can drive, for example, transportation, hoisting, even the storage of the modules and the installation sequence. So these are all important aspects that have to be taken into account from the design stage so that we can ensure that whatever we are designing is compliant with the constraints that we will have on site. And this also brings us the attention to how important it is to already have manufacturers and contractors involved from early stage, because that only at that point we will be able to have their input and really understand what are the constraints that we will have on site, for example, in terms of train capacity or site accessibility. Another important aspect, for example, is also about the forces and accelerations that the modules will be subject to in the temporary case from the moment they are manufactured to the moment they're transported to site and installed. Because those accelerations can potentially damage the modules. Think that in most cases the modules will come already with all the finishes pre-installed, and we can have brittle finishes such as marble for the toilet areas, and we need to avoid damaging those areas because damaging obviously will incur additional costs and time to fix those damages. Another case study takes us back to the Far East in South Korea, where Ramboll did a collaboration with Sampio. Sampio is one of the largest concrete manufacturers and precast suppliers in South Korea. In this case, Sampio approached Ramboll because they wanted to develop an innovative precast system, and they had particularly three requirements for this system. It had to be a prefabricated system, it had to be load-bearing wall system capable of also taking lateral forces, and the third point was to be able to be implemented for high-rise buildings. So what we did is that we looked at a system which we previously developed for non-seismic region. It's a wall system or double wall or twin wall, and we developed the design further to be suitable for high seismic region. This system includes two precast slabs which are prefabricated from the factory. Once precast, they are held apart by a steel lattice girder. So as you see, once it's prefabricated, there is a void in between the two slabs. At this point, the wall is transported to site where it will be installed. It will be put in its final configuration, and then the floor plate will also be installed. The floor is generally also precast using a half slab system. So at this point, in situ concrete can be poured into the gap, and by doing that, we achieve a monolithic joint. So you can see how by doing this, we achieve both the benefits of having in situ construction with a monolithic joint, which is very useful, especially in seismic region, together with the benefits of prefabrication, with speed of construction, quality pre-finished surfaces of the walls. So it is a hybrid solution which gives us the benefits of both in situ and prefabrication. As part of the system development, we also helped Sampio to develop a mock-up which will show the implementation of this double wall system in a smaller scale. And then the system was put in the context of a high-rise for a case study, which would be the new headquarters for Sampio. This is a mixed-use development, which includes an office tower, together with 2 office residential buildings connected by a podium. The focus for the case study was the office tower because it's the one to be fully precast, unlike the residential towers, which would be in situ instead. So what we did is that we made the tower fully precast and identified what different precast components we would be using. And we utilized the central core wall to implement the double wall system that we developed. That would provide the lateral stability to the building, and it would be the main lateral force resisting system. This was a very important assumption in the structural engineering philosophy, because it allowed us to release the rest of the structural components, such as columns and beams, from the lateral forces, which promoted standardization and repeatability. We also have precast facade and a common podium which connects the 3 towers together. Now, I would like to talk about research and development, and this is a very important aspect when it comes to fabrication. The reason for that is because what we are seeing currently in the industry is that prefabrication is speeding up very quickly. And we started off by having prefabrication, precast, now volumetric construction for low-rise buildings. And quickly, now we are seeing implementations for high-rise buildings in seismic regions sometimes. So we see the industry moving very quickly towards prefabrication. But often we also see that codes and regulations don't really keep up quite well with the speed of the industry. And also the academic world is struggling to keep up with that. There is not enough research in that. So it's important that we commit to doing research and development so that we can contribute by using our lesson learned, our experience, and further progress with the use of prefabrication within the industry for the future and pushing the boundaries and improving the quality. So as part of our commitment in research and development, we do collaborations with university. This is particularly a collaboration that we have done with the university, the Monash University in Kuala Lumpur, where we studied the behavior of high-rise modular buildings under seismic actions. So as part of this study, we did a performance-based design to really understand what are the activity requirements when it comes to the modular volumetric construction, and how does it work together with the main lateral force resisting system, which in this case was located in the 4 areas again. And even if we have a main lateral force resisting system, which takes the majority of lateral forces, we know that for high-rise buildings subject to earthquake forces, usually buildings undergo large displacements, which means that the modules, even if they don't tend to attract a lot of forces, they still undergo large displacements. So we have to ensure that the components of the modules can take those large displacements without failure, which is a compatibility displacement issue. So as part of the study, we did the research, we successfully completed the research, and this was published last year. Now, I would like to, before we wrap it up, draw some conclusions, and particularly looking at what is the key takeaways of this talk, but also what are the barriers for the implementation of prefabrication and the opportunities that we have with this innovative technology. Now, key takeaways. First of all, we have talked about how important and how such a game changer prefabrication is for the industry, and particularly for the use of high-rise implementation. And the reason for that is because it allows flexibility. That's because of the different system typologies, which can adapt to different building and different project requirements. But also, there are important design considerations, which we usually call design for manufacturing assembly. And those design considerations can be different from the design principles associated with conventional construction. And that takes me to the last point, which is the importance of the designer's role. Probably the most important point that we're making today, because the designer has to be able to design for modular, has to be able to design for for prefabricated systems and identify what is the most suitable technology that can meet the project specific requirements. In terms of barriers and opportunities, what we are currently experiencing is that there is an increased interest in modular and prefabrication, and this has been seen at all the levels of the value chain. But there are also some barriers which prevented the wider adoption of prefabrication. So there are a number of barriers that we have identified, that we have experienced with our projects, and maybe we can have a discussion after this talk, but this is just a summary that we have developed. So we have knowledge, first of all, knowledge gap. There is a knowledge gap which is felt really at all the levels in the project, from the developers to also the consultants. Sometimes they're not able to design for off-site manufacturing, but also even manufacturers and contractors, because sometimes they perhaps don't know how to use a modular system for high-rise buildings. The second point is about cost considerations. There is usually a price premium to pay when it comes to prefabrication, and that's usually because of the cost related to the setting up of off-site manufacturing capabilities, for example, for the manufacturer, and that can be seen as problematic or sometimes prohibitive for some stakeholders. Also, another important aspect is related to the appropriate collaboration models, and it's important to have the right models in place in order to successfully deliver projects. We can do a great design, but if we don't have those correct collaboration models in place, that can all go to waste. Because, for example, we may not involve the manufacturer right in the design process so that they can contribute with their system and integrate it within the design. Also, the approval process and regulation is another constraint, especially for those countries that don't have correct procedures in place for the systems. For example, that can cause delays and other risks in the projects. Also, supply chain development. We have seen supply chain developing quite a lot over the past years, but much more can be done. And if we can achieve that in the supply chain, that can just enhance further the use of prefabrication, for example, by cutting the cost further. Thus, price premium can go down because of the further development of the supply chain. We're also cutting the embodied carbon associated with the transportation. Also, we have a skill and workforce development issue, because there is more that can be done in order to upskill the workforce so that they can contribute to the prefabrication processes which require these high skills. Government support is another important aspect, because especially for those countries which are new to the technology, that price premium can be even higher, and having the government support can help to offset part of the price premium to further develop the use of prefabrication and modular within the country. And then last point is about market maturity. We are seeing an increased interest and acknowledgement of the importance of prefabrication within the industry by all the stakeholders, but overall, I would say that there is still a lack of market maturity in order to implement prefabrication at a wider scale. And by tackling all of these issues, addressing them, we can turn them into opportunities for the development of prefabrication in the years to come for many more projects. And with this, we come to the end of my presentation. I welcome any questions that you may have. Thank you.
Thank you very much. Very interesting presentation. Lots of examples. Thank you. I think it's no longer nice to have. We always facing pressure from our clients to start thinking modular early in design, even at the feasibility stages. And we've been asked difficult questions around cost, speed, and what's the return on investment, what's the advantage, is it better, is it? So there is pressure on suppliers, obviously, but also on design. It's a difficult question. And, the learning curve is really sharp.
Yeah. And I think it's very important that we get this interest from developers from already feasibility studies, because that's the point where we can add more value to projects.
Yeah.
When it's the very early stage of design, there's much more that we can do. We don't work with so many constraints which we would have otherwise later on. Sometimes we also see, for example, some projects developers, they want to convert into modular or into prefabrication later on, and obviously it's more difficult to make it work at that point because we have to probably really have constraint to the design and to other aspects that don't allow flexibility. It's important to see that, but you're right that the learning curve is very sharp because there is things are moving very quickly in the industry.
Indeed, yeah.
Yeah.
Thank you. Let's start with questions in the room here. Sanjit, go ahead.
Two questions. First of all, is there any special code requirements for modular build, especially the connections? Because I assume these are more like locking mechanisms, not the typical connections. So that's my first question. Second one is you mentioned we don't need to check for lateral forces in final condition properly, but during transportation, it may still be subjected to some wind or the other forces because of transportation itself. Is that something that's considered in the design of the module itself, or how do you account for the forces during transportation?
Okay, thanks for the questions. Yeah, so I'll start with the second question. Forces during transportation is an important aspect that we also take into account during the design. It's all part of the DFMA, design for manufacturing assembly. So we take into account of those forces. We have to understand how the module or the precast components will be transported. We need to know that. So that's where it's very important to have the manufacturer involved so that we have answers to the methodology that will be used during manufacturing, during loading on the truck, for example, and even during storage and hoisting on site. So we need to know these things. And by doing that, we will know what kind of accelerations, forces, the modules are subject to during these temporary stages. So we have to have the input, we have to work closely with the manufacturer so that we can know exactly what kind of scenarios the offsite manufacturing components will be subject to during along the way. So it's less standard, I would say, because you don't have like you don't just rely on the codes that give you the loadings. Instead, you need to really use your best practice and your experience on this type of technology in order to understand, and it requires a lot of engineering judgment. In terms of codes, there is not specific code dedicated to, for example, volumetric construction. There are guidelines. There are some guidelines provided in certain countries which identify the key aspects that have to be taken into account from a design, manufacturing point of view, installation. But there is no specific code, so we still rely on the building codes that we use for conventional construction.
Thank you.
Yes,
So I also have two questions. What is the name of the software to design the connection or to simulate it? And what kind of contract do you have in the case of OMC project? Is it like design and build with the contractor as your client, or traditional route with the ultimate one?
Thanks for the question. So in terms of software, we use finite element software, for example, for the analysis and design. We start with the global analysis. In that case, we tend to use EDAPS, especially for tall buildings. And when it comes to the intermodule connections, we do additional analysis and modeling, and we use localized modeling. The software which is very common to use is IdeaStadia, for example. That is very much used also for steel connections. So that's the kind of software that we use to do this additional localized finite element analysis and modeling, which is required to ensure the safety of the connections. And the second question
For the type of contract, is it like contractor stuff?
It's usually we need the involvement of the manufacturer from early stage, as we said, in order for them to contribute, and that requires early contractor involvement. It's a ECI approach, which is the design and build, if you like, and that can be, for example, for the modular components of the building. So usually it's important to have the main contractor also involved at the stage of design, and it could be a modular manufacturer which is also appointed on a design and build basis with an early contractor involvement, where usually the manufacturer contributes at the early stage in the design process. So the first phase of their involvement will be the design. So they contribute together with all the designers and consultants on board. they contribute in design, finalizing the design, and then there will be a second part of the deployment, which is in the manufacturing and installation of the modules as well. So in terms of model, definitely requires an early involvement through a design and build early contractor involvement kind of model.
Module to module is generally a rigid connection, and then your as the distance from the core or the lateral supporting system increases, your load increases the connection points. So, how do you account for the tolerances? Like, because I mean, even though you do modular, you will never get it for the zero tolerance. So, how do you accommodate that, and how different are the connections as we move away or move closer?
So tolerance is a very important aspect, and definitely there is a gap in between modules. There is a gap which accounts for this tolerances. Tolerance is an important parameter which has to be provided by the manufacturers so that we are aware of what is actually that they require in terms of installation tolerances, in terms of manufacturing tolerances as well. And usually the connections will then connect the modules at the discrete locations. So you don't have a continuous connection generally, especially when it comes to modular volumetric, and particularly for those modules that tend to use structural steel as a chassis type. So there are discrete connections which are located at the columns, for example, or the column to beam connection, rather than what you usually see when it comes to precast systems, where instead you may create more of a continuous kind of connection. But it depends on what systems we are looking at. You can have a continuous connection, and in that case, for example, when we do hollow core slabs and we do in situ topping on top, so that creates that continuity of the floor, which provides also the diaphragm connection and continuity. But if we use the modular volumetric with steel, often are discrete connections, and the connections will have to allow the transfer of these forces at the discrete locations in terms of in-plane and out-plane forces.
And in terms of tolerance, can we also say that the same principle applies as construction for construction? But the other part of the question is about tolerance.
Yeah,
Yeah.
the same principles apply, yes. The only difference is that when it comes to tolerances, as I was saying, there are important considerations with the installation of the modules that you don't have when you look at conventional construction. Because with conventional construction, you're constructing on site directly. So by having something which is pre-manufactured, you have to account for these tolerances in the installation. And you install complying with the tolerances. So you have to allow for a gap so that the modules can fit and you comply with the tolerance, but then you have to connect them. So the connections have to be compatible with that. The connection has to allow the joint between the components and still comply with the tolerance. Otherwise, you will have an issue during the installation process.
See, for tolerance to answer, BS-EN 1090 specifies two class 1, class 2. So here we go for stringent. So in normal construction, if 1 in 500 km, here we have only 1 in 1000. So there are two classes as per BS-EN. So we go for stringent. And to add, American construction industry, CII, they were the one during 80s, they came up with the concept for energy sector, for industrial plant, PPMOL, prefabricated, pre-assembled, modular, offsite. So they took idea from offshore topside fabrication and it was taken into industrial plant. So this type of modularization is already in the energy sector for last 30 years, and it is serving for site where we cannot send labor, difficult environment, difficult conditions. So like it is in the industry, they call PPMOL. So now it is PPVC in some part of the world called MNC.
Thank you, Anthony. Yes, please.
Just a quick question. First of all, thank you so much for this very important presentation. I have a question regarding the kind of design. So you mentioned performance-based design, right?
something. So I assume that your design is not a force-based design, it's a performance-based design. So for performance-based design, as I mentioned, you have to control deflection, but also the most important is the nonlinear behavior of the structure. So for that, for conventional structural members, there are recommendations by different codes like PMR or ATC, how to control the rotation of plastic hinges and so on. And for this type of special and specific type of structure, is there any recommendation? Is there any code that we can control the nonlinear behavior of the structure for performance, regardless of each level of performance? I guess that the level of performance is life safety for your structures, if I'm not mistaken.
Yeah. So, yeah, thanks for the question. So performance-based design is something that we may want to use depending on the project requirements. So we don't necessarily have to go down that route. If it's a seismic region, for example, for example, we have a good reason for which we need to go down that more complex route. For example, we want to overcome some of the constraints that the code provides in terms of height or other reasons, then we do the performance-based design. But it doesn't necessarily have to be as to be done like that. An alternative to performance-based design is a code-based design, which is what you're describing as the force-based, basically. And in terms of code-based design, we comply with the codes, which are the building codes, and ensure that the forces which develop within the modules comply with what the code requires, basically. Now, the reason why we want to do performance-based design sometimes is because if we have in a high seismic region, and for example, we have a tall buildings, usually using modular construction, we need to ensure that potentially the forces which develop as a consequence of the large displacements, so that the deformation compatibility issue, basically, those forces can still work for the modular components. And it can be challenging to analyze that using a code-based approach. So we have to do performance-based in order to really see what is the force associated with large displacement. And in that case, we need to do models to understand what is the sectional properties, the nonlinear properties, as you said. And the same codes that we use for conventional buildings still apply. We still use that, basically. And we just have to understand how to use the regulations which are provided by those codes and to apply that for the systems which we are designing in this case. So there are obviously different type of systems and connections that we are dealing with because of the system typologies that we are using, but the same codes will still be used.
Thank you. We've got a few questions on Zoom. I'll go through them. So the first one is which wind and seismic code is followed? I guess you have answered this question.
It depends on the country, but yes.
So basically similar to traditional form of construction.
Exactly, same wind and seismic codes we will follow the code in the country where the building is being constructed.
Sure. Another question from anonymous attendee. Great presentation. I must ask, what are the risks in terms of integrating the electrical systems that might later affect its maintenance in the long term? So this is about electrical systems. Do you have any experience?
Risks associated with the electrical systems. So as part of the MEP strategy for the modular systems, because it's very important we look at the design of the modules. I didn't really delve into the MEP aspects of this, but there is also all the aspects related to the modularization, the standardization of the modular of the MEP systems as well. And another very important aspect that we take into account is also the maintenance. So we need to ensure that the accessibility, so that the electrical systems, in case of any problem which requires ordinary or extraordinary maintenance, it will be accessible. So it's important to take this aspects into account. So there is already maintenance strategy which will be part of the prefabrication systems, which will also be part of the design.
Sure, thank you. A question from Mustafa Batiha. Thanks for the excellent presentation. It's about CO2 emissions. So do you have any data about the cost and CO2 emission of concrete prefabrication versus in situ construction? Some research has referred to the higher cost because of heavy crane transportation, model storage, etc., and more CO2 emissions as compared to the traditional form of construction. Do you agree?
This is a very good question. CO2, okay, the wider prefabrication obviously can use also different materials, and there is and that's probably the main advantage of using prefabrication is that as we said earlier, we can use more carbon-friendly materials as opposed to concrete. Now, this question is specific about precast compared to in situ, and I would say that the answer is there is not one answer. It really depends on the project. If there is a project where we can achieve the standardization, that can help to reduce the carbon emission. But if we try to fit precast into a building where we don't achieve that repeatability, then we may actually not achieve the benefits that we want, but instead it can become very productive and we can even increase because we have too many unique types, so that can increase even the carbon emissions that we are producing during the fabrication process. So there is a level of efficiency that we can achieve through the prefabrication if we can get that economy of scale. Yes,
Right.
that's about it. There is not so much saving probably in terms of CO2 if we just look at the comparison precast with in situ. That's very true. So not so much CO2 saving. CO2 is more about the opportunity for other materials. But one important, very important aspect that you can still take into account in terms of sustainability, and I know that this is not quite a question because the question is about CO2, but it's about construction waste. Because construction waste can still be minimized using precast. So while precast maybe doesn't get you to reduce the CO2 levels so much compared to in situ, can still help you a lot with the construction waste. And that can be another great benefit, which could be a driver for the choice of using precast as opposed to convention.
Right, sure. Yeah, there's a weightage to every saving. So a question from Somar, can we use PPVC for a building in high seismic zone?
Exactly, that was one of the case studies. Basically. Yes, we can definitely do that, but we have to ensure obviously that the building will comply with the code requirements and the level of safety that is required by code. We can do that in low rise, we can also use in high rise, and that's the new limits that now we are seeing with the implementation of PPVC for high seismic regions, with, for example, implementations in Saudi Arabia and other countries.
Thank you. I hope you can take a few more questions. A lot of questions are coming. So Mohammed Rehan is my colleague. In one of the slides, there was peak ground acceleration and response spectrum analysis that you displayed with some damping figures. Is the system critically damped or over damped? Maybe Rehan, you give us a little bit more.
This one is a bit specific question.
Yeah,
I'll tell you that in terms of damping, the same process of damping that we use also for steel structures, conventional structures could still be used.
Okay. Okay.
So
Thank
there are
you.
not specific considerations when it comes to different damping compared to conventional.
Okay, here's a question from Hari Krishna. How are the secondary effect due to imperfection addressed in this design? Since these are large modular units, you may not be able to achieve the same level of precision as you do with the conventional system.
Yes. Secondary order effects and imperfections is a very important aspect, especially when you look at the implementation of modular construction for tall buildings. Now, this is another important reason why we often use reinforced concrete core walls together with the modular constructions, because we use the core walls, the verticality of the core walls to set back the volumetric part of the building so that it will be better. So effectively, at that risk, you don't accumulate additional imperfections as you install the ones, because you have the verticality of the core, which sets you back to the main point. And that's how usually the imperfections are managed for buildings using modular volumetric construction.
All right, thank you. Final question on zone. Do we have particular scenarios where prefabricated modules can compromise the structural stability of the overall structural system? that should be addressed in the design.
If there are, can you repeat the question?
I think it's a.
So it is like the module in which you have, it also can contribute to later load resisting system. So something there.
Can it compromise the structural stability
Okay, no, it's-
question and so detrimental effect?
It's a bit of a, okay, interesting question. I would say it doesn't compromise, it shouldn't compromise, if it's
Yeah.
well designed, right? It should not compromise. Obviously, we ensure as part of the design process that the modules can take any forces which are within the modules. Now, it can contribute, that's different, right? Because if you can it compromise, it means can it do negative to the stability? It shouldn't. Can it help? Can it contribute? It can also, it can contribute. Usually, you don't want the modular volumetric part to contribute significantly to the lateral stability. And the reason for that is because the more it contributes, the more it attracts forces. And if it attracts a lot of forces, that means that the components of the modular volumetric part of the building will tend to be upsized. So you lose the standardization that you want to achieve. That's why we want to release it from lateral stability. In the case that a cold wall system, for example, is not sufficient as a lateral stability system, we can add additional systems. Could be a bracing, could be additional portion of the business where we can provide additional lateral stability. But it's good to have the modules which do not take so much lateral forces, because the more they take, the less we standardize, and it can defeat the purpose of using efficient modular volumetric construction.
Sure, thank you. Yes, please.
Okay, I asked you a question quickly. It's a general question. In Canada, recently, because of the immigration rate, price of houses went up 2 to 3 times more. And now the country is thinking about accelerating construction process. And one option, of course, is pre-construction, considering the fact that they don't have enough number of workers in country, and they cannot allow workers like Dubai to come for projects or temporary projects or temporary, let's say, construction booming. So they are thinking about pre-construction, especially for the cities that have access to sea and shipments are kind of facilitated. This process. So outsourcing now is the thing that they are basically thinking about. Of course, some people say that it's expensive. And I'm wondering that, first of all, what for this situation, outsourcing from China, India, or so, do you think this kind of plan idea is feasible? And if that country specifically goes for outsourcing, at what level outsourcing should be done? At element level, volume level, so large parts of the building should be shipped to the country to save demand for workforce. So I was wondering, what's your opinion on this?
I think it really depends on what is the key driver. If the key driver is, for example, demand for housing, because they don't have enough housing and then they have to do that quickly, then that can justify the use of prefabrication, potentially modular volumetric or other typologies. So if the demand is the key driver, that can justify even a price premium that you may have to pay, because it generally is not cheaper. It can be more expensive, but perhaps that can help to achieve the target. So that can justify the reason why you may want to go down the route. Another problem could be reliance on manpower, because you don't have enough manpower to build on site in Canada. So by doing that, you can solve the problem by doing off-site manufacturing, which can be done in factories located in other countries, wherever they could be. So you can solve the problem related to reliance on local workforce. You can solve the problem with the high demand and the time requirement also to get it done quickly. And usually it does come with the price premium to pay for that. So obviously it has to be within the budgets and has to be obviously taking into account very effectively. To what extent that can be done, that was your second part of the question. It depends on the project requirements. So we have to understand the project typologies. We need to really identify which parts of the project are more suitable for which type of technology. If we try to force modular construction, into a project which doesn't really meet the, for example, the criteria of standardization that we can potentially achieve, that can take us to not being effective, which can potentially be very bad because we can have a, for example, something which is very expensive, it can increase the body carbon, it can have it can be no good compared to conventional construction. So it's important to understand the project and also to see how much the project can be adapted, perhaps to a efficient use of modular construction.
Not forgetting carbon, that increase with the long transportation. Yeah,
Thanks very much for the presentation. It's excellent. Just have two questions. The design of the modules at the bottom obviously can be attractive for journalists. So what's the difference between the columns that we want this ground floor at the top? Second question is just on the facade there. The elements of the facade installed afterwards locally because it covers over the joints.
Okay, the question about the columns is a very good question because I touched on this very quickly in the presentation. I was saying how we standardize the module sizes. So we have only 5 module sizes in terms of chassis size, but within each module type, we have substructural topologies set. And for example, we divide the building height into zones, and we have the 3 zones, for example, in order to optimize the column weight, for example. What we wanted to do is to keep the module sizes as they are. We use the SHS columns, for example, and we just changed the thickness of the walls. By doing that, we kept the connections standard because it didn't affect how the inter-module connections work. But at the same time, we managed to optimize the weight, halving the weight going all the way up. So we found really how to optimize, reduce the material, but keep it standard the connections, which was very important. So that's how the optimization of the columns, and also it works similarly also for the beams in case there is a reason why we have to also optimize the beams. That's how it works. In terms of facade system, facade really depends on the project. Sometimes it's pre-installed from factory, sometimes it is not, and it's just installed on site. For the project that I showed earlier during the case study, the majority of the facade is already pre-installed, but there are strips which are left in between the modules, which will then be attached on site. And that's how we create waterproofing for the.
yes, could we please?
So it's not a structural technical question, of course, I'm an architect, so I can surely come more on the research and development part, which I'm interested in because as architect, we tend to move away from MMC when we have a nice building that cannot be really thought in that way, and maybe it's a bit more organic, it's not 90 degrees, twisting and stuff like that. We like play around with our buildings, and now like more you see like higher building being twisted, being like a big hole in the center, and they try to play around. And all I see like when we talk about research around MMC, all I see papers made engineers, which is logical, right? You want an engineer for construction and MEP part, but I think we need to pair them with an artist or an architect who can push the limits of the engineers. Because this is also my question to you, is that do you think that these researchers or these development for the future should tend to go to more, maybe there's an organic module that if you place it in a certain way, it can form the whole building in a certain scale, it can be twisted or non-standard or 3D printed modules that can be assembled in a certain way, like a puzzle. But I don't see a lot of this creative side being invested in these researchers. I don't know, I'm just asking you for your opinion on that and how we can move forward to maybe instead of architect designing the building and trying to fit where the boxes would go and design it from an organic style and go around with the whole building. Just because
No, it's I think it's an interesting point that you're making, and it really depends on the purpose that we are trying to do with the research and development, but definitely also challenging the layouts, perhaps with something which is more bespoke. It's also an important aspect that can be explored through the research. that can come to the point that we, for example, could compare some parameters between a more conventional and less conventional layouts to see what are some benefits or what we can achieve, for example. But usually all of this research is really about understanding the performance, and as you're saying, it's much more engineering focused. So understanding the performance, whatever we feel like there is a lack, for example, in the codes, in the regulations. So we have to do further research in order to validate, understand better so that we can improve those aspects. So tend to be much more engineering focused. But there is also an aspect related to that actually can be further explored as well.
And this small second question about stands. So when you're designing a building and then suddenly there's like a big stand with no columns, more like vertical structure inside the building, inside the space, for some reason, is it part of your MMC or you need it for on-site or? When you're talking about like a large, like this room, for example, or like places which is like.
Yeah, it depends on what prefabrication technologies we are using. If you're referring to volumetric, particularly, usually you don't use volumetric for a very large space because obviously that will give you a lot of problems. Even if you imagine you prefabricated a component like this, how are you going to transport
or like 2 parts?
So often what we have is that perhaps we could have a volumetric construction for the upper floors, and then when it comes to this, to have a transfer so that you can build using different systems, whether it's in situ or it's still prefabrication, but it could be more of a kit of parts kind of system, for example. That's usually more suitable.
To add, we can have a module where we have a temporary wall. So like if I put in this classroom, so I will make during transportation temporary bracing for this wall. And when I come here, I put in a place and temporarily what I do. And if you allow me to answer his first question about architecture, I would add, see, we will be having a talk by William B. Baker from SOM who designed huge people. He will be giving keynote speech for iStructure, and he has inspired many engineers. He collaborated with architects. So his answer for your first question, like which state. So he said, like if like as an engineer, if someone comes architects, can you fix it, this building, which is a twist state or incline? Yes. But if I can build something with available construction material, we have to think about future generation. To fix something which is a bend or twisted, I will require more concrete, more steel. I can fix it. We as a structural engineer, we can build it. But if something which is simple, which can provide accommodation to millions, why we should not go for a straight solution? So this was the answer. Will Baker informed. Like structural engineer and architect, they should come together to find out simple road path. Why do, like if something can go in a straight line, why do bend?
Thank you, Hamad. I think this is the normal day-to-day.
It's much more of a project-related kind of scenario rather than research, right? But yes.
I think it's actually nice when they push the boundaries. I think that structural engineer, I was thinking, is it pushing the body or driving them crazy?
Pushing the button, it's maybe not in my imagination.
Last question. Two questions.
One is, when we go for volumetric, obviously steel becomes a preferred choice because it's better. Is there any situation where, because you said you can use concrete or timber, so is there any situations where concrete is a better option in volumetric? That's one. Second, as you mentioned about DM giving approval in principle, can you elaborate a bit more on that? Is it based on certain guidelines or is it based on?
DM approval.
Yeah. Or you had a discussion.
Okay, sure. Concrete PVC versus steel PVC. The short answer is that there is an advantage in cost usually using reinforced concrete PVC as opposed to steel. Usually it tends to be cheaper. A lot depends also on the country, but generally it's cheaper. But obviously you increase the weight, which is the main advantage of using reinforced concrete modular volumetric construction. The weight goes up a lot. Generally, it's almost twice as much the weight. So it is much heavier. And that obviously brings a lot of issues when it comes to the logistics. So because of that, it's it's becoming more and more popular to use steel rather than to use reinforced concrete. But in a lot of countries, reinforced concrete, PVC, is being used. And the main reason is the weight, the cost. The cost is the main reason because it's cheaper. And then the problem is probably the perception that reinforced concrete gives you better performance. For example, in terms of acoustics performance, there is a perception that you will get, especially for residential buildings, you will get better return compared to steel. So that's another reason. But they're used, both materials are used, and they have their pros and cons. In terms of DM approval, what we did is that we developed the system and we went through this process of getting the in principle to municipality approval for this multi-story modular building system. And that included showing all the aspects. It wasn't just structure part, but it was also the MEP and architectural, just to show how the modular volumetric fully pre-finished would work in principle for the system. And obviously that would require, in terms of process, getting the in principle approval from DM means that they acknowledge that the system works in principle, but you will still need to get further project approval as you go on with a specific project to show that you comply with the code requirements and everything else. But they are at least familiar with the system so that we'll streamline the process moving forward. It won't take us long because they already know how the system works in principle. That's a procedure which is also followed in other countries, in Singapore, in Hong Kong. So there is this in principle system approval. The authorities require that so that later on they will take much shorter to approve than the system when it's implemented on the project, especially if it's used in a standard way. If it's obviously used in a non-standard way, that could potentially require extra time.
Thanks.
Thank you very much. Excellent presentation, thank you. A lot of engagement, lots of questions. We might need part 2. Because there are more questions that we could have, but that's fine.
I'll be
Thank you
happy
very
to
much.
Thank you. Group for
There are some refreshments as well.
I will just not.